Answer your email, Connor, yes, but let's set it up after this afternoon. That way I know which ones. Or binder. Not doing so well. That happens. Well, I guess it's about time to begin here. Any questions before we get started today? All right. Well, as you may remember, we were working on the fundamental theorem of calculus. And just to briefly remind you of how this works, I'll zoom in on this short solution here. If we are given a definite integral, such as say 4x over this interval from 2 to 4, we can compute this integral using the fundamental theorem of calculus part 1, which is the version of the fundamental theorem of calculus that we use the most. So I find the antiderivative, which is 2x squared. I plug 4 into 2x squared. I plug 2 into 2x squared, and I take their difference. That's all there is to it. Of course, this is a super easy problem, so it's very short. We did a bunch last time that were much longer, involving, sines and cosines and complicated things. But it all works the same. And then I even went so far as to actually prove the fundamental theorem of calculus. I don't know. I just kind of felt like I was in the mood to do that, so I did it. But now it's time for me to introduce you to another sort of part or version of the fundamental theorem of calculus. This one is used nowhere near as often. It's kind of this forgotten part of the fundamental theorem of calculus. So what is it? Well, in order to answer that, I need to go over the concept of an area function. So an area function is a function that you get from integrating another function. And I have a picture here that kind of shows it, but I have a Desmos animation that I think is a little bit better. So here I have this blue curve here. And what I can do is I can compute the signed area here between the blue curve and this interval here. Do you see that nice shaded region there? Yeah, yeah, right there. Now the question is, what is the area of this region? And if I were to go a little bit further here, you could see that this blue region, it's pretty close to about half of this 1 by 1 square. You see it's about half of that 1 by 1 square. And so that suggests to us that the area here will be approximately 1/2. Now there's this red curve here, and if I click on this point or click on a point near it, you can see that, oh, I'm sorry, this is not a square. This is a rectangle. It looks like a square to me. It's got a width of 1 and a height of 0.5, right? So half of this rectangle would be about 0.25. And so here on this red curve, I roughly record what the area is at that point. So here at about x equals 1, my area is pretty close to about 0.25. It's a little different than it. And the idea is that as I move this point along, or maybe this point along, or there, okay, I was just thinking about it. I move this point along here. This green dot gives a shaded region, and the y coordinate of the purple dot gives me the area of the shaded region. Does that make sense? So as I move this point along, for some reason, Desmos is not liking me right now. Let me refresh this. I think I probably broke something. Yeah, as I move this along, you can see that when the area gets really small, the y-coordinate on this purple point also gets really small. And as I move this point further and further out here, you can see that the area is getting larger and larger. And sure enough, the y-coordinate on the purple point is getting larger and larger. You'll notice, however, that once I pass 4 here, suddenly my y-coordinate here starts to go down. It decreases in value. Why does the purple point here decrease in value around 4 and past it? Right, we're taking a negative area, right? It's a signed area, so it's subtracting this area from it. And we can continue doing this, and you can tell that right around the time that purple dot crosses the x-axis, that tells us that this area here, this positive area, is canceled out by this negative area. And so f here is the blue function, and the area function is this red function. So the area function is basically what you get when you look at all these different signed areas under this curve. And so let's go back to this slide. Here I have a pretty similar setup. I have a function f of x, and you can see that what I've done is I've plotted a red curve here that I call capital A of x. And the idea here is that, you know, if this is my x value here, A of x is going to give me the signed area here in this orange color. And if we wanted to define what A of x is, it's technically this. It is we do the integral from little a, our starting point, to x of our function f. Now we have to be a little careful here because it's a little confusing here to say a to x of f of x dx. At least I find that confusing, too many x's running around. So it's customary to use a different letter here, but the idea is that this is a function, but the thing that is changing isn't necessarily the f, but the upper bound of the integral x. And so this is our function a. Now, one of the interesting things we can do, well, first of all, I have a neat fact here. The area function at little a right here, it's always going to be 0. You can see that in the Desmos animation. If I move this over here right there, yeah, if I'm not really getting any shaded region, the area is 0, so the area function is 0. And so this is always true. Important to keep in mind. And I'll get to example 2 in just a second, but I want to tell you what the fundamental theorem of calculus says. It says, suppose you have f that's a continuous function, and you make an area function from it. So you're like, I am going to make an area function. There it is. Well, if you wanted to take the derivative of the area function, it's incredibly simple. It's just f of x. That's it. The derivative of the area function is literally just f of x. And there's a lot of different ways you could say this. One way of saying this is a of x is the antiderivative of f, or is an antiderivative. Another way of saying a prime of x equals f is to take the d over dx symbol here and then plop your a of x in there as an integral. All of those are equivalent forms. And so I'm going to take a picture of this real quick and we'll work on example 2. This is called the fundamental theorem of calculus, part 2. Like all movie franchises, sometimes the second part just isn't all that interesting compared to the first. Sometimes they are. Back to the Future, that had a good part 2. Star Trek had a good part 2. But that's about it as far as I know. So imagine I had the following function. I had f of x is square root of x to the fourth plus 1. And imagine I defined an area function. The area function is, say, the integral, let's say from 0 to x of f of t dt. If I wanted to, I could plug in right here. That's fine if you disappear, Sydney. Thanks for letting me know. And that's what the area function will be. So if that's my f of x, this is my area function. And imagine you're asked to find the derivative of the area function. You got to find the derivative of the area function. I will show you the solution by FTC2. A prime of x is equal to, all right, does anyone see what is a prime of x equal to? According to FTC2. Yeah, that's it. It's equal to f of x or that. Done. Shortest derivative ever. I don't know. Do you feel like this is like a bad joke? Like there should be more to it than this? Basically, if you have an area function and the function that this f inside it is there, the derivative of that area function is just the thing that's inside there, except if there's t's here, replace the t's with x's. That's it. That's all there is to it. Let's do another example, one that may look a little bit more elaborate at first. Here, I'll write it this way. Find let me just make, oh no, this is one of my problems I give you. Let me change it. We'll do secant t squared plus 5 there, dt. All right. Suppose you were asked to find the derivative of that ugly thing. You may have an impulse to want to say, find the antiderivative, right? You may say to yourself, well, I gotta find the antiderivative of secant t squared plus 5, plug in at x, subtract 1, plug it at 1, subtract 1, and then take the derivative with respect to x. But no, you do not need to do that. It's much dumber than that. Much, much dumber. Here is the solution. What we do is we think of this as our f of t. That's the thing inside there. That's our f of t. And this integral that contains this f of t, this is our a of x. And so what we're being asked to do is we're asked to find basically a prime of x. You're asked to find the derivative of this thing, and this is an area function. That's what you're being asked to find. And so by FTC2, the derivative of a of x is, all right, does anyone want to take a stab? So close. Megan said t squared plus 5 here. That's almost it. Almost. Very, very close. X squared plus 5. Yeah, that's it. That's the only difference. Yeah, there you go. Okay, that right there is the fundamental theorem of calculus part 2. That's all there is to it. I kind of like this version here. This one's really nice. If you're asked to take the derivative of an integral from a to x of f of t dt, skip the integral, skip the derivative, it's just f of x. That's it. This is like cutting in line. Okay? It's like you're supposed, in your mind, you're like, I have to do these computations. But nope, I'm not going to make you do them. Now, I have some challenging problems here. One of which I want to change briefly. I'll change this to, I don't know, 2 there. All of these problems use the second fundamental theorem of calculus, the part 2 version. Some of them are straightforward. Others, such as part B, are less straightforward. But why don't you try out part A? See if you can find the derivative of the integral from 0 to x of sine of t squared dt. Does anyone think they figured out part A? What is it, Lee? Correct. You did it. All done. Does anyone think they know the answer for part B? It's a little different, isn't it? Do you see how they're different? This one had an x at the top, right? And this one has an x squared. In the back of your mind, you may be wondering, does that matter? And so you might just try guessing. That's what I would have done if I were you. I'm going to put a question mark here. I would have guessed it was this. That's what I would have guessed. Just be like, oh, just kind of the same thing, right? Just this is you let t equal x, right? Here. Well, maybe you let t equal x squared there. That seems plausible. That turns out to be wrong. But it seems plausible. So let's go over how you actually do this type of fundamental theorem of calculus problem. So let's do part B here, because it is a little sneaky. But don't worry, you'll have a shot at redemption in part C. We have this integral here. And I do not know its derivative. Basically, this thing here, this x squared, this is ugly. Screws everything up. I don't like it one bit. What I would like better is to have this integral, which of course is not what I'm given. I would have much preferred to have this area function from 0 to x sine t to the 8 plus 4 dt. That would have been nice, right? Everyone agree with me there? Because if I have that, I know its derivative. I know the derivative of this is by FTC2. I know this is sine x over x to the 8 plus 4. But unfortunately, I'm not asked to take the derivative of that, am I? I'm asked to take the derivative of this ugly thing. But let's take a look at the ugly thing for a second. Sometimes ugly things have a little bit of beautiful in them. You just have to have an open heart. That's all. What's the main difference between this ugly integral and this one? That x squared. This ugly integral, turns out it's a pretty integral. But instead of an x being plugged in, it's an x squared plugged in. Does that make sense? And so if I were to take this a of x and I told you, hey, tell me what a of x squared is, you would say, well, in order to figure that out, I have to look at wherever my x's are. Well, there's only one x there, and I would have to replace that x with x squared. And so, yeah, sure enough, this thing that I want to take the derivative of is just a of x squared. Thus, when I'm asked to take the derivative of this ugly thing, 0x squared sine of t over 2 to the 8 plus 4 tt, I'm really being asked to take the derivative of a of x squared. Does that sound good? All right, I can take this derivative. Now, there's a rule I have to use to take this derivative. Do you see what rule I have to use? Not quite. I have an x squared plugged into another function, the good old chain rule. I'll take the derivative of the outside function, keep the inside the same, and then multiply by the derivative of the inside function. Does that sound good to you? And now, here's the great part. I know what a prime of x is. It's this thing. And so I can figure out what this thing is. I can just take this expression here, and everywhere I see an x, I replace it with this x squared. And so I'll get sine x squared over x squared, the 8 plus 4 times 2x. And that would be my answer for part B. The trick, let's just recap what the trick was. The trick to this type of problem was to recognize that what we had was an integral that the FTC2 could not help us with. There was this x squared. So we considered instead the function FTC2 could tell us something about the function where there's an x instead. We then looked at the ugly thing and saw that there was a little bit of that area function hiding in there. And then we used the chain rule to take the derivative of both of these. And when we took the derivative of both of these, we could then use FTC2 to get a final answer. All that to say, our initial guess for part B wasn't too far off. I said it was sine x squared over x squared to the 8 plus 4. Almost the exact same thing. The only difference is I had to multiply by a 2x. And so I can fix it now. 2x. And now it's correct. Here, maybe I should change this one. Here, why don't you try this? We are gonna bust the whiteout. Did you know OneNote has whiteout? There it is. There, we'll white this out. Perfect. And maybe I'll make this 1 to square root of x there. That's a little bit. Try out that one. See if you can find what that thing is. I'll try to get all of this on here. I'm gonna freeze the screen and move stuff around real quick, okay? Except for the online students. You get to watch me move stuff around here. Uh-oh. Right there? Okay. There we go. There we go. Okay. Hopefully you can see everything okay. You're young. Your vision shouldn't be failing yet. Like that's a square root of X, by the way.
Is it just gonna be like 3/2, like times whatever that is?
Uh, 3 over. Yeah, there's gonna be something like that. Yeah. Not quite that. You probably should write it out. Uh, don't do this in your head. Write it out like I have here in blue. Oh, how would you do it if the X was on the bottom? Remember that Cindy's asking. Remember that property where if you can swap the bounds on the integral, if you stick a negative sign in front of the integral, you can use that. There's there's a few different tricks, but I'm my goal isn't to be too tricksy today. Just a little. Very good. Oh, I have homeworks to give back. I'm almost ready to give your exams back too. They'll be outside my office this afternoon. Connor's almost ready. Almost ready. For those of you who cannot see, Connor had Tommy. Well, I'm not supposed to talk about your medical conditions, am I? Is this a private thing? He had Tommy John surgery. Are you a pitcher? You are a pitcher. Oh gosh. What are you doing to your arm? What sort of pitch are you throwing? A lot of curveballs. Okay. Yeah. Whew. Lift that arm around. Okay. Yeah, curveballs are. Yeah. My brother-in-law can actually throw a knuckleball pretty well. That's that is a dying breed. There was a golden age of the knuckleball in the early 2000s with Tim Wakefield. I don't know if you ever watched him pitch. He started out as an outfielder who practiced the knuckleball, and he was just incredible with it. Like he was just unhittable at times, especially if it was windy outside. It was just like there's no way you can hit it. And for those of you who don't know, most pitches in the pros will get in the high 80s and 90 miles per hour. The knuckleball, you can actually throw at about 60 miles per hour, and the pros can't hit it in many cases. It's amazing pitch. Another obscure pitch is the ephus pitch. You should try that one. Have you ever seen the ephus pitch? Yeah, that one is. Was it? Did someone throw that recently in a game a few years ago? Yeah. The ephus pitch is like you're throwing pop-ups to someone, except you're actually trying to get it to go over home plate. The problem is the ball comes down so fast, people aren't like used to it. I think it's like one of the few pitches where you can throw a strike and to have it hit home plate. Like, okay. All right, let's talk about part C. So part C, very similar. I'll just put it here. I forgot what the fun. Square root of cosine. There we go. There we go. So here, the ugly thing is right there. You see that nice and ugly? And so even though that's what we have, we're going to look at A of X here. A of X is going to be the almost exact same thing, but with the cosine t cubed plus 3 dt. Looking good? That's what that is. And we can figure out what A prime of X is. What's A prime of X going to be?
Square root of cosine.
Yeah. X cubed. All right, that's the only part of, yeah, there we go. That's it, right. Isn't that great? Okay, and so what we want to do before, when we did this problem, we said, oh, this ugly integral here, I can write this as A with an X squared plugged in. What can I write this one as? Yeah, yeah, and I'll say A with the square root of X plugged in. Yeah, you could just do it that way. So that's what that is. And so if I'm asked to take the derivative, as I am in this problem, of square root of X cosine t cubed plus 3 dt, I'm really being asked to take the derivative of A with square root of X plugged in, or as Keaton said, A with X to the 1/2. And I'm going to do A X to the 1/2. All right, what's the derivative of this? Or what rule should I use? Chain rule, right. So I'll take the derivative of the outside function, keep the inside the same, and then I have to take the derivative of the inside function. What's the derivative of the inside function? Oh, no, you're taking the antiderivative. What? X to the negative 1/2. Yeah. And now I just plug in here. I know, isn't that awful? I went and taught you how to do antiderivatives, and then I'm like backwards, forwards, backwards, forwards. Ah. And this would be your answer. You could simplify it a little bit. That's just a x to the 3/2 right there. But that's the basic idea. Doesn't really look like an X, does it? I don't know what that character is there. Okay, that looks better. All right, let's take a look at part D. This one's mean. What do you notice about this integral in comparison to all the others? It's got a 4 instead of an X. Yeah, so you may be wondering what is the derivative of this? And the answer is 0. Should probably explain why. Why is it 0? Well, are there any x's here? No. That means this is a constant. And the derivative of a constant is 0. This is a constant. You could, in theory, figure out what that value is, in theory, and it would give you just a number, maybe like 7.2. Oh, 0.96. And then if you said, what's the derivative of 0.96? You'd say 0. All done. So be aware of these problems. I'll usually sneak one of these on an exam. Some poor student will try to do the antiderivative of a function that you can't do the antiderivative of. So don't fall for that. There's one other thing I need to discuss here in number 4, and I put it as a group work problem, but I'm probably just going to do it more as an example. we've been discussing how to find antiderivatives of functions. Like if I said, what's the antiderivative of 2x, you'd say, oh, that's x squared. Or what's the antiderivative of cosine? And you'd say it's sine. We have these ways of getting really nice antiderivatives. But it turns out that area functions are always antiderivatives, always. And so you can technically always, technically, you wouldn't necessarily get credit in my class, but if someone said, what's the antiderivative of this function? You could say, well, here it is. It's just the area function. There, that's an antiderivative. Sure, why not? It's true. The second fundamental theorem of calculus tells you it's true, but it's still kind of weird. So for part A here, we're asked to find an antiderivative, f, which has the following, this is called an initial condition. When you get into differential equations, oh boy, we'll do lots of those. But the idea here is I'm going to let my f of x, in this case, be an area function for this. I'll say, oh, this is from a to some value x of this f of t dt. And I'll just take my f of x here in part A, replace the x with t cubed, or replace the x with t. And that would be an antiderivative right there. It's not a very useful antiderivative, but it's an antiderivative, right? Now, the other requirement is I want f of 3 to equal 0. So we want f of 3 equal to 0, which is to say we want this integral from 3 to a of t cubed plus 1 dt to equal 0. Now, can anyone think of a value of a, little a, that'll make that happen? 3, yeah. All right. In that case, you're just integrating from 3 to 3, right? And so, thus, this function I was looking for is simply the integral from 3 to x of t cubed plus 1 dt. How's that look? I mean, these questions are kind of weird, aren't they? I mean, they're just not like the other problems we've done. We could do something similar for part B. For part B, you might be able to figure it out right away. I'm going to set up an integral from a to x, and I'm just going to integrate this function. Sine of cosine of 3t now, not x, dt. And what should my a be? Pi? Yeah, that's right. Congratulations. You've figured out the trick. That's all there is to it. Yeah, this will be an antiderivative of that little f of x. The second part of the fundamental theorem of calculus guarantees it. The derivative of this is that, and if I plug pi into here, I'll get 0. Now, here's something interesting that we'll get to later. There are some functions that are really hard to take the antiderivative of. Like, for instance, if I were to give you the following problem, let's say I were to ask you to find the antiderivative of 1x squared, 1 over x squared dx. You probably could do that. You'd say, well, this is x to the negative 2 dx. And I know that I just need to add 1 to the exponent, right? And so I'll have an x to the negative 2 plus 1, which is negative 1, over negative 1 plus a constant, right? That's not so bad. But if I change it just a little bit, if I say, okay, find the antiderivative of 1 over x, things start to get a lot uglier real quick. Let's say to yourself, okay, well, I need to take the antiderivative of this, so I should add 1 to the exponent, right? I'll get an x to the 0, and then I have to divide by that exponent, 0. Do you see what the issue is? Yes, this is really bad. This is super bad. No, it's not constant. What was that? It'd be 1 over 0, which isn't really like, what is that? Yeah, it's kind of undefined. If we're taking a limit and you get 1 over 0, you have an infinite limit. This doesn't seem very good. And so basically what we're going to do is later we will define an antiderivative for this. For f of x equal to 1 over x. And that antiderivative, it has a special name. It's called the natural logarithm. It'll be an integral like this. Just like that. And so although this may seem like a silly thing to do, to say, oh, I can define an antiderivative, it's just, the integral of 1 over t from some value a to x. This is precisely what we end up doing when we cannot find nice antiderivatives. When we can't find a nice antiderivative, we have no choice. And so there's this whole area of mathematics called special functions. And, I brought this encyclopedia book last class, but I didn't show it to you. But it's a book of just integrals and antiderivatives. It's math. It's about 1,300 pages. And there's no text, no reading. It's just formula after formula, giving you all these different formulas. And so finding antiderivatives is a very difficult problem. So you have to have a lot of resources to do that. Okay. Any questions on all this stuff? Ready for some real life applications of integrals? I know I am. Let's do some real world applications. Net change. All right. We've worked on problems like this before, but let's take a look at it from a slightly different perspective now. Imagine you have a car that drives along a highway at a non-constant velocity. All right, so that car, its velocity is changing as it goes. Hopefully it doesn't go backwards ever, but it's traveling down the road. We're going to let S of t denote the position of the car on the road in miles at time t and hours. So we have this function S of t that gives the position of the car on the highway. And we'll let V of t denote the velocity of the car at time t. All right. So what is the displacement of the car? Well, the displacement, as we know, is just you look at its position at time 3, you look at its position at time 1, and you take the difference, right? That's what displacement is. But there's another way to think about displacement. Imagine for a second that you weren't told what the S of t function was. Like nobody bothered to tell you, but you did know the V of t function. Can you figure out the displacement without knowing S of t? And the answer is, well, yeah. Here's how it works. What we do is we take the integral of the velocity function. So we do this integral from 1 to 3 of the velocity function. And the velocity function, if you recall, is really just the derivative of the position function. So S prime is the same as V. And so when I do this integral, I just need some function that when I take its derivative gives me S prime. And so, well, S is a great answer, right? And so when I use the fundamental theorem of calculus part 1, if I were to say know what this S of t is, I could plug 3 in and 1 in there, and I get the exact same answer. And so I kind of have two ways of computing displacement now. One is to explicitly determine what my S of t is. and the other is to just do an integral. And it turns out that they're morally the same process. Figuring out S of t and figuring out this integral involve pretty much the exact same type of thought process. But I'll show you it using this integral approach. So let's do an example that illustrates this. All right, let's suppose we have a particle that travels on a straight line, as particles tend to do. And suppose it has the following velocity. Its velocity is given by this function v of t, and it's going to be t cubed minus 8t squared plus 15t meters per second. So we're told something about how fast the particle is traveling at time t. And t is in seconds, the distance is in meters, and so the velocity is in meters per second. Let's suppose you're asked to find the displacement. Find the displacement between time 0 and time 6. One nice way of writing that is we're going to find the displacement over this interval from 0 to 6. Okay, so here's one way we can do it. We can use FTC1. We're going to set up this integral from 0 to 6, v of t dt. And I'll just plug in what my v of t is. It's that t cubed minus 8t squared plus 15t dt. And now I just need to take the antiderivative, plug in at 6, and plug in at 0. So the antiderivative of t cubed, what's that? I'll give you a hint. It's not 3t squared. T to the 4 over 4, yeah. Or 1/4 t to the 4th. How about this one? Correct. And then this one will be 15 over 2t squared. That's the antiderivative, and I'll plug in at 6 and 0. Now, as an aside, S of t is this as well, but with a plus c added on. If we wanted to figure out what S of t was exactly, we'd have to figure out what that plus c is. And basically, this method allows you to avoid bothering with that part of the process. So it can be kind of convenient for that reason. So what I'll do is I'll plug in, and as always, I love parentheses. 6 to the 4 over 4 minus 8 over 3, 6 cubed, plus 15 over 2, 6 squared, minus 0 to the 4 over 4, minus 8 over 3, 0 cubed, plus 15 over 2 zeros squared. That's just silly. Only this term ends up producing anything, and if you used your calculator or something to that effect, it's just 18. So it'll be 18 meters. That's the displacement. That's it. So that's how we can compute the displacement of a particle if we're given its velocity function without having to explicitly determine S of t. Okay, yeah, it's kind of like a neat little trick. Yeah, whatever. We can work with that, right? Yeah. Any questions on this? Okay. So that's just one particular type of problem. We've been working with problems that involve, velocity and position quite a bit. But calculus is useful for more than just that. It's true that calculus was mainly developed to solve physics problems, but it turns out that derivatives occur in all sorts of settings, both in physics, aside from velocity, but in the real world in a lot of different ways. And so we want to we sort of want to generalize this idea of displacement. Displacement is like an actual physical thing, but we want something similar to it that can be applied to different settings. And so we're going to introduce this idea of net change. So imagine S of t is just a function that gives some quantity at time t. That quantity could be the position on a highway. It could be the amount of water in a bucket. It could be the value of a stock. It could be a person's blood pressure at a given time. Uh, it could be just about anything, right? S of t is just it's some quantity that's changing that changes with time t. And then we can look at its derivative, S prime of t, and this tells us the rate at which that quantity is changing. So maybe water is leaving the bucket. That would tell us the rate at which the water leaves. Maybe the stock is going up at value. That would be the rate at which the stock is increasing in value, and so forth. The net change is like displacement. If you want to know the net change over an interval from t1 to t2, you just do S of t2 minus S of t1. But sometimes we're not given the function S. And if that's the case, the net change can also be computed by integrating S prime of t, which is like the velocity. We integrate S prime of t from t1 to t2. So let's do an example to illustrate net change, something that's not related to the velocity of an object. So this will be example 2. We have a balloon is filled with helium. Big balloon, by the way. You know, first, I wasn't sure how big balloons could be filled up with helium, but there are weather balloons. They can be pretty big. So pretend this is a huge one, okay? A balloon is filled with helium at 9 a.m. And I don't know if you've noticed this, but helium balloons lose their helium. It then leaks a huge amount of helium. It leaks T over 10 plus 1/4 liters per hour thereafter. So basically you fill it up, it's going to lose at least 1/4 liters per hour. But as time goes on, it starts leaking more and more. It just starts to escape. Where, in this case, T is hours after 8 a.m. After 8 a.m., after 9 a.m. All right, you can ask this question. How much helium is lost between 1 p.m. and 4 p.m.? So you're basically told the rate at which things leak helium. And now you want to know, well, how much am I losing between 1 p.m. and 4 p.m. specifically? So how do we approach this problem? Well, usually what you want to do is start off by identifying what your S of t is, at least conceptually. You don't have to figure out what S of t is, like a formula for it, but you want to know what it is conceptually. And we kind of have two things we could measure. One is we could attempt to measure how much helium is still in the balloon, which is one thing. But we're not really asked about how much helium is still in the balloon. Another quantity we could measure is how much helium is lost. And that's exactly the sort of thing we're being told information about. And so in this instance, it makes sense to let S of t denote the amount of helium lost. Amount of lost helium. From 9 a.m. to time t. And with that in mind, we can then take a look at what S prime is. Does anyone know what S prime of t is going to be? This one we're actually told. Thank you, Keaton. Yes, all right. You were like, I wonder how long this guy can wait. Oh, it's so long. So long. It's one of those things they try to teach you when you first start teaching. They're like, whatever you do, don't let them get away without answering a question. If you just have to stand there the whole time, just stand there the whole time. I could do that. All right, yeah, that's S prime. I never liked it when the class didn't answer questions when I was a student. Yeah, I just didn't like the awkward silence. So even if I didn't know the answer, I just say something, you know. I'd say like the answer's 5. No, no, it's -20, Brandon. And just sort of, live with the consequences of giving like wildly incorrect answers. Just sort of be like, whatever, I'm fine with that. Hey, Mike. All right, so we're gonna let ST denote the amount of lost helium from 9 a.m. to time T. All right. And so we got to figure out this net change. What's the net change? How much helium is being lost? Net change from 1 p.m. to 4 p.m. Well, we're going to have this integral, right? And we're going to integrate S prime of t dt. We know that. The question, though, is what are our bounds of integration?
Must be 4 to 7 this hours after.
Yeah, it's 4 to 7, not 1 to 4. Remember, t is hours after 9 a.m. So 1 p.m. is 4 hours after 9 a.m. And 1 p.m. is 4 hours after 9 a.m. and 4 p.m. is 7 hours after 9 a.m. And now I'm prepared. Now I'm able to start computing this problem here. Okay, so I'm going to have this integral from 4 to 7 of t over 10. Yeah, we can do t over 10. That's fine. Plus 1/4 dt. And now I just need to take an antiderivative. All right. What's the antiderivative of t over 10? It'll be a t squared over something, right? What's a something? 20, yep. And then the antiderivative of 1/4. Nope. T over 4. I know, isn't that awful? It's like I told you the story once, right? When I taught myself how to write backwards. Yeah, it's like that. It's like that. Suddenly you don't know which letter goes which way. You're just like, oh no, I can't remember. Right, right. And so now I'll plug in, I'll get this 7 squared over 20 plus a 7 over 4 minus 4 squared over 20 plus a 4 over 4. And now I compute 2.4 here, 2.4 liters. That's how much is leaking out now. That balloon is not going to stay up in the stratosphere forever. Definitely not. Okay. So that's the idea behind net change. We've got how many minutes left? 7. Okay. I just have a bunch of problems for you to try out. We've got the displacement of a particle. We've got a tank of water leaking. And then we have the production of widgets. Back when I made this problem, nobody had the notion of a widget. A widget was just this generic object. And now widgets are things you put on your phone, right? Yeah, sort of. So go ahead and try that out. Oh, and just so you know, we have a real exciting one. We have an indecisive squirrel. The car's coming toward it. You got to figure out whether the squirrel survives. You got to stick a few of these, like problems that get the pulse pounding. Yeah, you're setting it up just right. And yep, very good. It's really just, oh dear. I don't know how. She is. So it's four t, not t to the fourth. So that makes it just the antiderivative will be 2t squared, which is a lot easier to work with. Oh, that's a fancy little blender thing. Oh, looks nice. Okay, yeah. All right, how's it going?
I think it's set up correct.
Okay, all right. I'll let you continue on. Good, good. Dr. K will be so pleased when you move on to Gen Phys. Do these integrals. Good, good. Ah, for number one, I just ended up doing this integral right there. 4t minus 3. And the antiderivative is 2t squared minus 3t. So I get a 2 times 5 squared. That'll be 50 minus 15. That'll give me 35. And I'll have an 8 minus a 6. That'll give me a 2. And so I'll have 35 minus 2, which is 33. So my displacement for part one is 33 meters. I think that's about all the time we have. I don't think I can go over number two in the next minute. We'll do the rest of these. There's lots of interesting problems, but this is a pretty short topic. We'll go over how to compute distance using integrals, distance traveled. I don't know if you remember that kayaker problem last semester at the very beginning. I gave you all these like estimate questions, estimate this velocity, estimate the distance traveled. The whole goal is for you to be able to solve them all precisely by the end of the course. Okay, online students, any questions? Nope, you're all set. Okay, I'll see you folks later. Bye.